So this is known as the allylic or allyl carbocation. It has a positive charge here and a double bond over here. Okay. Now, this structure is inadequate for describing this allylic carbocation because there's a resonance structure. And the resonance structure looks like that. Okay. So simple bond line isn't going to give us a good description of this carbocation simply because it has a resonance structure, and when you think about where charge is distributed on this ion and you do the hybrid's going to look something like this. Remember, we use these dashed lines. And then I'd use partial to indicate partial positive on this side and partial positive on this side. Now, in this particular carbocation, if we're talking about an attack of a nucleophile, remember nucleophile would come with a pair of electrons, I would get the same structure from either one. But this kind of allylic carbocation shows up in all kinds of structures. So if it had been showing up in something like this, okay, that would have a resonance structure too, and it turns out the resonance structure looks like this. And I'm going to go through like how you do it really quickly, because it's important that you'd be able to draw loose structures, and then when you do resonance structures, you don't go through the whole process again. You move electrons around to see what the other resonance structures are. So if a nucleophile came in to attack this molecule, like you put it on paper, you attack this molecule, all right? The nucleophile can actually attach at two different places. Remember, the nucleophile will come in with a pair of electrons, right? And it will form a bond with that pair of electrons. And it could form a bond either here or here. And in fact, if you draw a structure that looks like this one and expect it to have the nucleophile attached at this point here, most of the time you'll be wrong. Most of the time it ends up attaching at this point here. So you can have a structure that you draw and think, oh, that's where the product's going to be. But you have to think about, we'll talk about resonance contributors and what causes ions to be stable. You have to think about stability of the resonance structure to determine where the major product is. Turns out what controls where things add on this one has to primarily do with temperature. At high temperatures you get one product, and at low temperatures you get another. So that's going to introduce a whole nother facet into predicting products of chemical reactions. Okay, I am going to try to squeeze that chapter in somewhere during this semester. There's just one section out of chapter 17 that I want to get in, but we'll see what happens. Okay, couple of things. Let's look at the hybridization of the central atom first. The book talks about steric number. That's in the language we use at City College, and I think at Willow and Reedley, is we talk about groups, electron groups. So if you look at these, if you look at this allylic carbon, or the central carbon of the allylic carbocation, what's the steric number there? Okay, how many groups are on there? So the first thing you have to think to yourself is, oh, oops, I got to fill in the hydrogen. It's missing. So there's 3 groups that are on that atom. So the steric number is 3. That means it's sp2 hybridized, right? So this guy's sp2 hybridized. What's the steric number here? By the way, you will stop figuring out steric number. You'll stop figuring out steric numbers eventually, because you're just going to look at it and go, oh yeah, that's what that is. It's sp2. That one's actually sp2 as well. because carbon needs to make 4 bonds. There's not a charge there. Remember, we talked about how charge affects the number of groups. There's not a charge there. So there's a hydrogen here and a hydrogen here. So this is also sp2. Okay, last one. We're going to figure out the hybridization of the carbocation end. So first of all, what do you need to do first to figure out what the hybridization is? Figure out how many groups there are, right? So I know that carbon's supposed to make 4 connections, right? But it has a +1 charge, so it really only needs 3 connections. So it's got 1 to a carbon. These are the other 2. So what do you reckon? What is the hybridization then? What is the hybridization of this carbon? It's also sp2. So a general rule is to be involved in resonance, okay? All the atoms involved have to be sp2 hybridized. Or you could have an sp hybridized atom as well, but they have to have some unhybridized orbitals for the electrons to move through. When we draw resonance structures like this and we talk about, oh, there's a double bond here, or there's a double bond here, right? The way these electrons are moving is they're moving from the unhybridized orbitals to form the next pi bond. So you notice I have a pi bond, sigma and a pi bond here. I have a sigma and a pi bond here, right? So what's happening is these electrons are somehow forming the pi bond on this side, and then these ones break away and they go up into be one of the lone pairs. In order to form a pi bond, those are only formed from unhybridized orbitals. So the hybridization of atoms involved in resonance has to be either sp or sp2. sp3 can't be involved in resonance structures. Right? So what kind of carbons are sp3? If any of them that have 4 groups, okay? So hybridization is only resonance is only present on hybridized sp or sp2 hybridized atoms that have available p orbitals for the electrons to move around in. So I'm going to write that out. Wait, I'm writing. So resonance only occurs on atoms or through atoms that are sp or, more commonly what we see, sp2 hybridized. Maybe I should make that too clear. So that means, or that's because you need unhybridized orbitals allow the electrons to move. That makes sense?
Yeah, so sp3 it can't be because those p orbitals are
Yeah, those p orbitals are all hybridized.
empty.
It needs empty p orbitals or p orbitals that can be made available. And you'll see how that comes into play in a little bit. Okay. Okay, so let me see something really quickly on this slide. Yeah, I'll just write it here. So the question was, can I explain again why sp3, right? Oh yeah, so unhybridized orbitals are what the electrons are moving through. Okay, that's how pi bonds. Remember, to have a pi bond, right? And remember, when you draw resonance structures, most of the time, all you're seeing is double bonds moving around, right? And that's the way we think about it in general chem. Oh, I can move this double bond here. I can move this double bond here. But a double bond is made up of a sigma bond and a pi bond. The sigma bonds never change. If you change a sigma bond, it's not a resonance structure because you're going to break the connection between atoms. Right? Yeah, so you can't use an sp3. sp3 get involved in chemical reactions all the time, but they don't get involved in resonance because when you do that, it's no longer, by definition, not resonance. Principles are still the same. Electrons are moving around. Okay. All right. So this is what I said. If you think about the molecular orbital perspective, if these are all sp2 hybridized, each one of them has a p orbital. These overlap in molecular orbital theory to form a bonding molecular orbital. That's the conduit which through electrons can move through a structure. So very large, like 20, 30, 40 carbon chains, where you have all sp2 hybridized carbons, act as electrical conductors. You can actually like put a voltage on one side of them and get the electrons to move through the pi bonds. Okay.
Because they're all like connecting?
Because it's a because in the molecular orbitals, what you have is a series of interconnected orbitals that you can push electrons through those orbitals.
Mush together and form like a phase.
Yeah, well, we'll see how it happens in later chapters, actually. We'll go through the details. There'll actually be lots of orbitals that are formed. When molecular orbitals form, if you have like 6 atomic orbitals, you get 6 molecular orbitals. 3 would be bonding and 3 would be anti-bonding. I don't know if you remember all that mumbo-jumbo we said in Chem 1A. But through those electrons that form on the molecule, you can push electrons through them. Okay. All right. I'll skip over this because I'm going to try to cover this in another chapter. But this is the picture of the orbitals that you get when you hybridize, or not hybridize, when you produce molecular orbitals from the 3 atomic orbitals. This is the bonding molecular orbital. We have non-bonding electrical orbitals, and we also have anti-bonding orbitals. The big difference between these is no nodes in a bonding molecular orbital, or actually, when we find this out later, more bonding interactions than anti-bonding interactions. And here you have lots of nodes, and that's what makes it an anti-bonding orbital. You have more anti-bonding interactions or nodes than you do bonding interactions. Okay, so we have a whole section on that later in the semester. Okay. So this is the allylic. I drew this up already, so I'll just go over it. So we represent an allylic carbocation as having 2 structures. This is one resonance structure. This is another resonance structure. And when you take these 2 and bring them together, this is what we call the resonance hybrid. You have 2 contributors. 2 contributors to give us the resonance hybrid. Okay. Yeah, and I put a little note here. The analogy in the book is not correct. Nectarines are peaches without fuzz. And we live in the Central Valley. We should know these things. All right. So we call this process of being able to move electrons back and forth, or move charge back and forth. We call this whole process delocalization of electrons. And delocalization of electrons allows molecules or ions to be more stable, okay, because they span a bigger distance. What does that mean? That means the charge density, which you would normally expect to find on one atom, is now distributed amongst a lot of atoms, okay? And remember, what does charge do to molecules in general? Makes them unstable, makes them want to stick to things and form bonds with things. So if you take a molecule that has resonance and allow the charge to spread around, that allows the molecule to be more stable. We call that, that term that we use for that stabilization is often referred to as resonance energy or resonance stabilization. Okay, so what I'm going to teach you now is something called curved arrows. Like, what's the most expedient way to draw resonance structures without having to rethink through like how many bonds are on each thing every time, okay? So curved arrows, and really this is like, if you can learn this and this makes sense, right, it's going to make 80% of the rest of organic chemistry easier. And the stuff it'll make easier is the hard stuff. So you have to master this skill. And the more you practice, the easier it'll get. This illustration down here, okay, shows you how the curved arrow works. The arrow starts, that's the important thing, the arrow starts where the electrons currently are located. And then what happens is the arrow ends where the electrons will end up. Not in space, but either on a bond or on an atom. Okay? In the case of chemical reactions, it's usually on a bond, but on an atom. But in the case of resonance, it's usually in the bond location where you're expecting to find those electrons. So if I like obey the curved arrow that's there, right? Then I can draw the resonance structure by redrawing the skeleton. And then just drawing the new bond that was formed. And the new bond that was formed in this case will be here. Okay, now something's actually wrong. So, Shelly, you got any money on you? Is that your phone?
Yeah. Oh,
I'll use that
yeah.
I'll use that instead. Okay, what happened?
You took it?
I took it, so you don't have it anymore, right?
Yeah.
So if this, okay, now I give it back to you. Now we're sharing it, but it's a pair of electrons,
Okay.
and I'm going to take it.
You just took my electron too.
What happened to you?
I got a charge.
What charge did you get?
Angry because you took my electron.
Yeah. No, think positive.
Positive.
Yeah, you're positive, right? If you take an electron away, right, then the charge should be positive over here. Because what you did is you broke the bond that was here and moved it over here. Okay? Now there's a whole series of rules, and we're going to go through the rules like how you do these things. But one of the important things to recognize when you draw resonance structures is the charge is conserved on either side. So if you had a positive charge when you started, total positive charge when you started, you need to have a total positive charge when you finish. If you have neutral total charge, that is, you take the formal charges and you add them all up and it comes out to be neutral, right? Or it doesn't have any formal charges, it needs to be overall neutral when you're done as well. Doesn't mean the number of charges will be the same. It just means the totals have to add up to be the same. All right. Okay. First rule of resonance and arrows, okay? Don't break single bonds. Because that's not resonance. When we do chemical reactions, we got lots of chemical reactions where we form and break single bonds. Because by definition, right, when you do a chemical reaction, that's rearrangement of bonds. But for resonance, you can't do this. Okay. Okay. Second rule. By the way, we already talked a little bit about this, right? Resonance occurs for electrons existing in overlapping p orbitals. Okay, now if you're in the second row of the periodic table and the most common or hydrogen, okay, never exceed the octet. And that kind of makes sense. It makes us happy. So you notice this is a bad arrow. Why is that a bad arrow? Because if I were to draw a structure from it, and you need to follow through on these things when you do them, you're going to end up with that. Okay, now this carbon, if you did formal charge really quickly in your head, would be negative, so I'd have to put that in. What's wrong with that? It violates the octet rule. So it's pretty simple. First rule is don't break a sigma bond. Second rule is don't violate the octet rule for carbon and his friends in the second period and for hydrogen. Well, it's not really the octet rule for hydrogen, but you know what I mean. Same thing's true for this one, and the same thing's true for this one, because nitrogen and oxygen can't accept another pair. The only way that could happen is if this atom could somehow get rid of a pair of electrons in the resonance structure, but this one can't do it. Is this one good or is this one bad?
It's good because it'll be double bonded with the 2 bond pairs.
So let's see. First thing you have to figure out is what's over here, right? There's a hydrogen, so this is also bad. So there's nothing good on this slide. Another general rule, okay? If you're in the second period, try not to have less than an octet. Okay? You can violate the octet rule by having less. Okay? And carbon is the one that does that the most for us. In resonance structures, it will often have less than a positive, less than 4 bonds. But not usually. Okay. What does the hybrid look like for this? Yeah, so you have a little bit of, this is neutral, right? But in the resonance contributor, they'll be negative on this side and positive. These are both resonance contributors. They'll be positive on this side. We tend to think of this as the structure, but it is the resonance contributor as well as this is, okay? So there is a hybrid that comes between these two, and it's going to be something like this. Well, it'll be something like this. And I'll talk about it, but this one's not so bad in the sense that oxygen will have the negative charge and it's more electronegative, if you remember some of those rules. We'll go over that stuff still. This is one of the reasons like molecules like acetone are so polar, even though they look like they shouldn't be that polar. It's because in the resonance hybrid, you put a negative and a positive charge on opposite ends of the molecule. That creates a relatively large dipole. You have to show, okay, in resonance, in drawing resonance structures, you have to show formal charge. So here's a resonance structure. What does the question mark look like? So let me draw a skeleton for it next to it, and then you guys help me fill it in. So what is, oh, and I'm missing that lone pair. I'll put that.
Is this rule 3 or 4? No, just a note.
It may just be a note. There are several. I think the book lists it out as 5 rules or something. What am I going to do here? Yeah, this tells me I'm gonna have a double bond, right? So right between here and here, I'll have a double bond. So I can do that. Now, here, it's a little bit sloppy because the arrow is actually going to what we would think of our head as in the sigma bond, but it's not really. It's going to the pi bond, okay? So one of these bonds will go away. Now, what makes up a bond? Electrons, right? And in the case of a sigma or a pi bond, it's a pair of electrons. So on this carbon, I'll have a pair of electrons. And now what we have to do is we have to take care of formal charge. So the oxygen is supposed to have 6 electrons, right? But it has 1, 2, 3, 4, 5, so its charge is positive. And the carbon is supposed to have 4, but remember, there's a hydrogen here still. That is, the hydrogen that was here didn't suddenly disappear. And if it helps you, draw the hydrogen there before you do the resonance structure so you don't screw the charge up. Right? So this has 5, so this has to have a negative charge. Okay?
So the one you just drew is a resonance of.
Yeah, it's the question mark, but I didn't want to write on top of the question mark. So these are both resonance contributors. The hybrid, right, would have a partial positive charge on the oxygen and a partial negative charge on the carbon that where I've drawn the hydrogen out. Okay.
So formal charges can change between resonance?
Yeah. So, but what's the total formal charge over here? It's 0, right? Because there's none written. This is +1, -1, so it's still 0. So the total of the formal charges always has to be the same. Otherwise, you're losing electrons or gaining electrons. Okay, so there's a nice clean drawing. How would you draw the arrows in the reverse direction? So you do the opposite is what I heard. So you'll notice that there's a pair of electrons here that showed up. So I have to draw the electrons going back. So if I just do this, let me start it. Draw like that. That would create a bond there, right? I can't stop there. I've got to take that pair of electrons that I made this bond with and move it back to the oxygen. I'm inclined to just do that. As long as you start on the correct bond area and push it to the correct atom, that's all that matters. Okay? Do you want me to write in a different color other than black? Should I do purple? And then you could see what I wrote real quickly. It's an aesthetic thing, but I will do purple from now on. Yep. Is that different enough? Or maybe
Is there like green? I think green was down in all that.
Yeah, because I thought this was a carbon. I didn't see the green, so I thought
need a dark green, huh?
hydrogen was attached.
These projectors have such low contrast. It's like, might as well just be gray.
I think the first one, the purple is green.
Do the pink one. Purple.
The pink one?
What colors do you have? How about you read us the colors you got? And then we'll decide.
Well, I have a palette of colors like that. Right? It's tough. That's why I ask. I tell people I'm not color blind, I'm color stupid. So I just make sure everything I buy matches with blue jeans, which is just everything I buy. And then I don't worry about it. Occasionally, I will try to wear something that matches with my wife.
Hawaiian shirt.
Yeah, I was just gonna say.
Hawaiian shirts on Friday. That's what I have. That's my new thing this semester. It's a big deal. I'm not editing any of this out, by the way, so you'll get to listen to it again if you really want to. Okay. So there are 5 bonding patterns in which resonance occurs. Recognize these patterns to predict when resonance will occur. So what we're going to go through is what each one of these 5 different bonding patterns is and show how you push the electrons on each one, and then we'll piece it together to do larger resonance structures, okay? Do you want me to leave this up and you can copy down real quick?
You're gonna go through
Yeah.
each one.
I'm going to go through each one, but it's nice to have it all in one place. You also have it on a slide if you really want it, but,
Or just take a picture.
or you can take a picture. With the phone I will take from you. No, won't do that.
You have such a serious face, I can't tell.
I know, I do this to my children all the time. I do the serious face and I say something completely absurd and they just look at me like, what? Really? Like, no. Did just last night for something. I don't remember what it was. So allylic. Lone pairs, positive charge. Lone pairs of electrons adjacent to a positive charge. A pi bond between 2 atoms with different electronegativities. Conjugated pi bonds in a ring. That would be like benzene, okay? All right. So, really quickly, we have names for positions next to of carbons next to or on double bonds. So the vinyl position, so like vinyl record, that's how that's pronounced. Like the vinyl or the vinylic positions are directly on these carbons. Okay? And the allylic positions are next to a double bond or next to a pi bond. Okay? So if you have something that is an allylic anything, it has to be one removed from the pi bond. Okay.
Exact component.
Yeah. So you'll notice, just to make this better, I'm going to shade these in a different color. Oh, now that I have red, I will. But this will be highlighter. I'll do. Let's see. I will do. Ooh, look at that. Oh, that obliterated it. It wasn't supposed to be opaque. Anyways, this chlorine, right, is attached to the double bond. So what does that make it? It's vinyl. If it's attached to the double bond, it's a vinyl position, okay? And if it is attached, but now you notice that this, what's that? That's this is the vinyl position, so this is attached to it, so it's allylic, okay? So if you're one away, that's an allylic position. If you're on the double bond, then it's a vinyl position. So all the vinyl ones, all right, let me do this. That's vinyl, and then the allylic ones, this one. What about this one? It's too far away. Okay. This one is 2 away from the double bond. Okay. So this one is, and it's actually allylic to both the double bonds. And then this one is none of the above. So let's do that in like that. Okay.
So the orange is the vanillic, or
Yeah.
vanillic, and then the green is
Green are allylic, yeah. Okay. So you can have a heteroatom, and we talked that's something other than carbon. You can have a heteroatom on a structure. If it has a lone pair on it, and that atom is attached to the double bond, this is an allylic lone pair. Okay? So we can identify the allylic lone pairs because they're on the atom next to the double bond. They're not next to the double bond. So this one, on this first one, what do you say that one is? That's an allylic pair. What about this? Yeah, that's allylic. How about this? That one's allylic. What about that? No, that's a vinyl. Okay. This nitrogen? No. And this lone pair? Yes.
I'm confused. Before we were doing it as if the resonance structures were occurring, and now we're doing it as if they're not.
Oh, actually, so what we're doing right now is we're just looking at the way it's drawn, whether it's allylic or vanillic.
Right there.
Yeah, and really, as long as you recognize it's allylic, you're safe. Right? It's attached to the atom next to the double bond, and not on the double bond. Yeah, so these ones that I crossed out, those are both on the double bond. They're on the atom that's double bonded. Sorry, right? And this one is on an atom next to the double bond.
Are they? But they're not vanillic because they're.
So these are vinyl, and these are allylic.
There's not a CC double bond.
Doesn't matter. It's any double bond.
Any double bond.
Any double bond. Yeah, it's a lone pair, right, next to any double bond. I have to be really careful how I say next to, though, huh? But you guys kind of understand what I mean? It can be on the atom next to the double bond, or it can be on the atom which is double bonded. Right? On the atom that's double bonded is vinyl. And
Or-
on the atom attached to an atom attached to a double bond is allylic. Yeah, it's easier just looking at pictures, and then eventually you'll be okay. That's it. Okay, begin to recognize these things. So no and yes, right, for allylic. So now what we're going to do is we're going to draw some resonance structures. That one and not that one. Okay, so that's actually the next slide.
We see that the vanillic and the allylic switch.
So, what's that?
Are they going to switch the vanillic and allylic? That's cool.
Yeah, they'll switch back and forth. So what's going to happen on this, on the first one? The electrons move towards the double bond. Okay, allylic electrons move towards the double bond, and then the double bond breaks and pushes the electrons away from that position. Okay, not towards. So it's not going to go, I'll do this, and then I'll say, no, don't do that. You can't do that. Because now you're just piling all the electrons onto that central atom. You can't violate the octet rule. Okay, so that doesn't help you. So what you have to do, you can take these electrons and go like this. Now, if you drew it like this, it's fine. Doesn't matter. You're taking an electron from, an arrow from the electrons and pushing it to the bond space where it's going to be. Okay? So either of those would be okay. And now the double bond breaks, the pi bond breaks, and the electrons go onto that atom. If you draw the Lewis structure that comes from that, you'll end up with it looks like a little face, huh? Yelling at you.
It looks like a little frog.
That's what I trained you guys in 1A to do. Like, this is a face, and he's like smirking, and this is a, yeah. All right, so, let's do this one. Again, what's the pattern for an allylic lone pair? The pair of electrons goes towards the bond, okay? So I'm going to take that and go here, and then that pair goes away from the bond, the new bond.
So they don't, vanillic and allylic don't switch places. You're saying that
They, well,
can?
it can. So let's just move on. So now I'm going to draw the structure that you get from that. Oops, sorry. Too many zigs on one side. like that. And then what am I missing? Pair of electrons up here, and a positive charge and a negative charge here. But again, the total charges add up to be the same. Next one, which way do the electrons always go? They're going to go from here, right, towards the double bond. And then away from the double bond to the atom.
Are you only ever gonna have two little jumps? Or one little
Sometimes you don't even have two, sometimes you just have one.
But you don't have more than two?
Depends. Not on these early ones for sure. If you're going to show resonance, it depends on how, like sometimes you can push all the electrons at one, we call it pushing electrons. You can push all the electrons at one time and show where the final charge is, but sometimes you want to see where the intermediate charges are, so you just do steps of two.
So you just keep.
Yeah, and moving that pair of electrons. And I'll show you an example on the board, where or on a blank slide, where I take a long chain and I just push electrons down the chain. Okay. So that structure. Oops, that's not a. What do I got over there? I got another oxygen. So where are my charges? Negative on the top oxygen. Positive on the bottom. Yeah, I think you guys got it. So I'll skip the next two. You guys can do them. I'll just draw the final result so that you have something to look at.
Do these resonance structures like exist? The fact that they're little.
The fact that you can draw them, there's some orbital combination that can create them.
But with the formal charges that are created, which makes them unstable, do they even get to that point?
Okay, so yeah, not all contributors are the same. So in terms of stability. So what the hybrid actually looks like is a mixing of the contributors based on their stability. And one of the things we'll look at is what allows us to say this contributor is more stable than another contributor. Okay, so and then the last one. What do I got on there? I got two groups like that, and I have three lone pairs, negative charge and positive. So that's what you should end up with when you push the electrons around. Okay, I'll go on to the next thing. Now, you can also have an allylic positive charge, a carbocation. That last one, right, most of those they're either negatively charged oxygens or carbanions. You can also push a positive charge, and positive charge is like the easiest thing to push around. Okay? First of all, it already violates the octet rule. So you don't want to violate the octet rule by going under the octet, but if it's already starting that way, then you can do it. It's not a problem. So you can take this first one, right, and you take it and you push it to the positive charge. That satisfies the octet for this one, so that charge becomes more negative, or becomes zero because it was positive one before, and this one's losing the electron, so it'll become positive. This is the one that we did before. So we can do the same thing with this structure that's down here. Oops, sorry. This structure that's down here. Okay. But I'll do it in steps to show you that there are multiple resonance contributors for this. So I can move this one like that. Then what happens? Well, the framework doesn't change, right? But now I have a double bond here. I didn't move this double bond. So we're trying to show this in steps the way you would think about it trickling through the structure, okay? What's missing? Positive charge. And you get the positive charge on the side where I took the electrons away from. So you have positive charge here. And now what you can see is this pair of electrons, right, or this pair of electrons can move over to here now. So you have another resonance contributor looking like that. So I have another structure. And now what do I have? Positive charge on here. Now this kind of goes beyond the scope of what we're going to be talking about really today. But what's happened is I have three structures, right? Turns out this one's less stable than these two are. And I'll explain that to you like when we get to that section eventually. But the idea is if you were asking yourself, what does the actual hybrid look like? Because this hybrid's less stable than these two, there'd be more positive charge on this carbon and this carbon than there would be on this carbon in the hybrid. Okay? And that's just based on thermodynamics, and I'll explain it. If you want to know the explanation after class, I'll tell you after class, but it's a separate section later in the semester. Now, you can also have a lone pair next to a positive charge. And like a bond next to a positive charge, only one electron's involved. Okay. So to go back, so if you want to go back from here to here, you would draw something like this. By the way, try to draw two-headed arrows all the time. Two-headed arrows mean something different than a one-headed arrow. What do you think two heads mean? So by a two-headed arrow, I mean it's got this side and this side. A one-headed arrow looks like a hook. That's a one-headed arrow. Or like this. And they actually call them fish hooks because they kind of look like fish hooks, right? Not that fish actually have hooks. But we have hooks to catch fish. Okay, what do you think the difference is? What do you think two means? What? No. The two on the two-headed arrow means two electrons move. And if one means one electron moves, and where you run into one-headed arrows all the time is what we call radical chemistry or radical reaction chemistry. You hear about free radicals in your body. Well, that's how those get formed. Not both electrons move. One moves in one direction. One moves in another direction. They kind of break up from each other, and then they end up being really reactive. I guess that's more like dating than I thought. Oh. Sorry. It always boils down to like one thing. And this can go like this, by the way. Okay. Let me ask you really quickly, gut instinct, because we'll cover some of these things in assessing stability of contributors. Of these two structures, which one's more stable? One on the right, because it doesn't have any formal charges spread out all over the place, right? So you guys recognize a good structure when you see it generally. You may not always know why that's a good structure, but you might look at it and go, oh, that looks like a better structure than that. And it has to do with it being beaten into you when you were a young child. Okay. Chem 1A or even 3A sometimes got beat into you. Okay, so this is another instance where we have a lone pair adjacent to a positive charge. When you have a nitrogen that's got 4 bonds on it, this is known as a nitro group. And in a nitro group, if you draw the electrons moving, right, it's an allylic lone pair, in this case in the nitro group. Goes like that, and then like that. And what you get is a double bonded oxygen on the right, single bonded oxygen on the left, and something else down here. Ooh, that's horrible. I can't see those dots at all. Let me try this again. There we go, like that. Okay. Neither one's more stable than the other. So really, nitro groups are stable because it can delocalize that negative charge around the structure.
So the one on the right lost all its own pairs.
What's that?
The one on the right lost all its own pairs, but oxidated.
No, it has
Oh, sorry, it has 4, sorry. Got lazy. And then, there's actually one other.
Can the electrons from the double bond pull it triple bond?
Occasionally, but not on this one because the nitrogen already has 4 bonds. Right, so it can't pick up another. But you could do this. How would I get to that?
You have to lose more electron bonds to
Yeah, I would have to take that double bond and do this. So this would be minus, I'm just gonna draw the skeleton of it with the charges, minus. And since the original structure was 0 overall, it means the nitrogen has to be what? 2 plus. That is a resonance contributor, but what do you think about that one?
It's so unstable.
It's very unstable, so we call that a minor contributor. So I drew it small. Sorry, it's my own little joke. So this is a minor contributor. Huh. I was just thinking we could make an Ochem shirt. And you could say it'd be like contributing to the resonance of a minor. And I don't know what the picture would be, but
You should run them all.
there's some like thing that people get in trouble for. I can't even remember what it is, but it's called contributing something to a minor. But contributing resonance to a minor would be a good chemistry shirt, right?
Yeah.
Okay, so you have pi bonds between atoms of different electronegativity. That's another pattern that we see. And this is one of those ones where the octet rule gets violated by going under the octet. The example that they give down here is for acetone. Okay? And the electrons move towards the oxygen because the oxygen's more electronegative than the carbon is. Okay? That's the time where you generally see those kinds of things. So in this case, in the other example that they gave with the nitrogen, you could just follow the example, take the electrons from the nitrogen, pi bond, and push them back onto the nitrogen. So then in your other resonance structure, you have that, and then you have to deal with charges. What's the charge of the nitrogen? -1. You can always just look at the arrow going to the nitrogen, so it's going to have a negative charge. And then this will have to be positive because it lost the bond. The last pattern, which is fairly straightforward, but it's important to know, it's not much we do with it really at this point, is when you have conjugated pi bond systems or conjugated pi bond in a ring, okay? And all the electrons just move in a circle at the same time. It's like a dance, right? So you have all these electrons, and you could go left or right. You don't go clockwise or counterclockwise. It doesn't matter. Left or right doesn't make sense. Clockwise or counterclockwise. So this way we're going clockwise, clockwise, clockwise. Oh, that's counterclockwise, sorry. I was on the back of the clock, sorry. That was a joke. All the bonds moved. Okay. What type of motions do electrons actually have? Answer is none. Because they just sit in the hybrid. The orbitals of the hybrid, they don't actually like move around the way we treat them. Okay? Like where is the electron in the orbital? Is like the other equivalent question. It's in the orbital. So if they're just in there, they don't need to move. All right, so summarizing all of this into one handy-dandy slide, okay? We have the allylic lone pair, just to review, because I'm almost done here. I didn't finish, actually. I do need to finish this stuff. So I will be just a little bit behind, and I'll catch up next week, which means the homework. It's not, yeah, it'll be due Wednesday. Is it the lecture after? So it'll be Wednesday, because I'll finish it on Monday, right? So it just, you don't have, but work on it. This is really important, even if it's boring to you sometimes. Allylic lone pairs, right? Two curved arrows, electrons move towards the pi bond. Allylic positive charge, pi bond moves towards the positive charge. Lone pair next to a positive charge, it forms a pi bond. And between differing electronegativities, we violate the octet rule, right? Generally. Oops. Violate the octet rule, and you'll get a sigma bond, you get rid of the pi bond. And then those in a circle just move in a circle. So. Before we go, we'll cover this one. I'm not going to draw all the contributors, but we'll show the electron movements for all the contributors that we can. Okay? So let me section this off in regions. Call this A, B, and C, just so we have something common to talk about. What's the pattern in A?
I wanted to say lone pair next to your positive charge.
Yeah, so what are you going to do when you move the electrons? You follow the pattern for a pair of electrons next to a positive charge. When you draw that final structure, that's one of the resonance contributors. You would just like make that, right, as another structure. And then what about in B? Nothing. Sorry, because B was supposed to be down here. So what about in B is going to happen? It's what kind of pattern? Yeah, allylic lone pair. It's a lone pair of electrons next to a double bond. So the pattern is to take this, go like this, and then these go like that. Okay. There's going to be one more, by the way. And then what's the one for the nitrogen in sector C?
Is it,
It's the electronegativity one. So the electrons that are between the nitrogen and the carbon to its right will go like this. And then I'll draw a structure from that. Does anybody see what the other one is? There's one more that comes from one of the resonance structures, actually.
On the bottom right, that
Uh-huh.
bond can that go to the top?
Yeah. So what can happen up here is this can happen. Okay, so there was actually one more. But what would probably be drawn is first you would draw the one that I called B, and then that would happen following what I did in B. Okay. All right.
Why can the electrons move from here to form a double bond, and then the double bond move, and then these electrons go over here instead of on this side?
Oh. So why can't they go here? So how many bonds does that have to have?
The hydrogens that we didn't draw?
Yep.
All right.
Yeah. That's why. Okay, so we'll cover stability of contributors on the next lecture. That's section 211. You could read that, be good, and read chapter 3.